Hello and welcome to the video lecture on halogenation reactions of alkanes. এই video lecture we will look into the free radical reactions of alkanes where a hydrogen atom from an alkane is replaced by a halogen. And this is the very first reaction whose anatomy as well as mechanism as well as kinetics will be investigated in detail. So this will serve as a template for the rest of your course যেখানে আমরা এরপর SN1, E1, aromatic electrophilic, aromatic nucleophilic addition, elimination, etc. All these types of mechanism we will discuss. And those are polar reactions and this is the free radical reactions. But how to analyze a reaction, how to analyze the kinetics of a reaction, how to decide upon the rate, where to look when to decide upon the relative reactivities. This should be the template. So halogenation is defined as a reaction or process in which a halogen is included into a molecule and no other element is included. It is a very well-known reaction যে alkane কে যদি আমরা high temperature like 250 to 400 degrees centigrade or UV light expose করে chlorine বা bromine এর সাথে mix করে সেটাকে রেখে দিই, then it leads to the formation of halogenated alkanes and an equivalent of hydrogen chloride or hydrogen bromide is also formed at the same time. So if I represent my alkane as RH and my halogen as X2, then under the photochemical condition or heating condition where X is bromine or chlorine, I will get RCl or RBr along with one equivalent of HCl or HBr. So obviously one of the hydrogen is getting replaced by X and therefore it's a substitution reaction. There are quite a few observations here. Chlorine is found to be more reactive than bromine in this case. It is not generally very useful for fluorine or iodine. Fluorination is rather difficult to control. Fluorine itself is a very aggressive reagent, very difficult to handle, extremely exothermic reaction, therefore almost explosive in nature. So people generally tend to avoid that. Iodination, on the other hand, is a very mild reaction, and among all these things, among all the halogens, iodination of alkane is an endothermic reaction, and it is the least reactive of the lot, fluorine, chlorine, bromine এবং iodine মধ্যে, and that is why it is thermodynamically not very favorable to carry out this reaction. In general, it is the chlorination and the bromination that is what we are more interested in. Chlorination is also rather difficult to stop at the monohalogenous state. It generally leads to formation of polyhalogenated product where multiple hydrogens has been replaced. For example, take the chlorination of methane. When you do this thing at room temperature by mixing methane and chlorine and trigger the reaction photochemically, then you will get methyl chloride where one hydrogen is replaced by chlorine. You will also get dichloromethane, you will also get chloroform, you will also get tetrachloromethane. So all these mixture of polyhalogenated compounds you will get. And this is synthetically a nightmare because if you are looking to synthesize only methyl chloride, then you have to separate your desired target molecule from the rest of the junk. But industrially, this is a very important process because all of these can be fractionated, separated in a very large scale, and all of these has separate use, and sometimes the mixture itself has found application as chlorinated solvents in many cases. So industry likes this reaction, but not laboratory scale preparation is suitable. And if there are more than one type of hydrogen present in the alkane, then they are also found to be replaced by the incoming halogen, leading to formation of different organochlorides. For example, আমরা যদি isobutane নিই, it has got like two different types of hydrogen. One hydrogen, the red one, that's the tertiary hydrogen attached to the tertiary center. The other hydrogen, that is the blue one, that is HB, that's a primary hydrogen because it is attached to a primary carbon. There are only one red hydrogen, but there is only one red hydrogen, but there are 9 blue hydrogens. And if you treat this with chlorine under photochemical condition, you get two products. Replacement of the red hydrogen will give you tertiary butyl chloride. Blue hydrogen replacement will lead to formation of isobutyl chloride. Make sure you understand the tertiary butyl and isobutyl grouping, the connectivity. The same thing will happen with bromine. but there are a couple of things which we note here. First of all, chlorine reaction is happening at room temperature under photochemical condition. The photochemical condition is not enough to brominate this isobutane. The reaction can only happen at 127 degrees centigrade. Therefore, definitely bromination reaction requires more energy. In other words, chlorine is more reactive, bromine is less reactive. Okay. And look at the product distribution. Again, red hydrogen replacement leads to the tertiary butyl bromide, blue hydrogen replacement leads to the isobutyl bromide. But the percentages of the two products are drastically different from what you see in chlorination. In chlorination, you see 33% TBU chloride, isobutyl is 67%. So the major product is isobutyl chloride, which is arising out of the replacement of the primary hydrogen. But more than 99% of the brominated product is the tertiary butyl bromide. So the replacement of the red tertiary hydrogen accounts for the majority, overwhelmingly majority of the product. And only less than 1% of the product is arising from replacement of the more abundant primary hydrogen. So this gives you another clue that bromination is definitely more selective. Whereas chlorination was more reactive, chlorine was more reactive, the selectivity of bromination is much greater. That is because in chlorination you are getting the mixture of two regioisomers where there are significant amount of both regioisomers. So chlorine, when it arrives, it chooses to react with the red hydrogen or the blue hydrogen, more or less, it's happy to react with both. It reacts with some at a better rate compared to the other, but it does not completely neglect any particular hydrogen. Bromine, on the other hand, is very choosy. It almost does not react with the 9 and statistically more abundant blue hydrogen, but chooses to react with the red hydrogen, which is only 1 in number, but bromine chooses that statistically less abundant tertiary hydrogen way more compared to its reaction with the blue hydrogens, which are like 9 in number. So there is a general there should be a general consensus among you looking at these two reactions. This chlorine activation energy of the whole reaction is low, that has to be more reactive, but chlorine with its high reactivity is also less selective. This is very much reminding of the reactivity selectivity principle in organic chemistry, which is a grossly simplified and overgeneralized principle, but sometimes it will work. That something which is more reactive is less selective and vice versa. So chlorine here is much more reactive, bromine here is much more selective. We will have to investigate that why this is so. But let us take one step at a time and investigate the chlorination of methane. That is the simplest hydrocarbon that you can think of. And then we go on treating this thing with chlorine. Say in presence of heat or light, we should get CH3Cl and HCl. The reaction will probably not stop here, but if you want to synthesize the CH3Cl almost exclusively, then you must use a huge excess of methane and a limited supply of chlorine, so that chlorine does not get the opportunity to react with the product CH3Cl, but due to the presence of the excess methane, it reacts almost exclusively with methane always till it gets exhausted and you get CH3Cl. Obviously there will be like excess methane and you have to separate CH3Cl from methane, but that's a different issue altogether. Obviously one equivalent of HCl will also be produced. Now there are certain observations which are listed below that we can see while doing the chlorination of methane, and they all point to one general direction, that these reactions are not polar reactions, not like nucleophilic substitution, SN2 or something like that. That we have discussed a little bit when we are discussing kinetics and thermodynamics. So when we mix chlorine and methane and we keep that thing in dark without heating, nothing happens. So no reaction. In the dark, you can make the reaction go by heating the reaction mixture, then the reaction will happen. You don't even have to heat the reaction mixture if you bring it out onto the sunlight or heat it with a visible light of a proper wavelength. and then the reaction will happen. The light that you are using to trigger the reaction, that has been shown independently to cleave the chlorine molecule into two chlorine radicals. So here is your first clue that the photochemically triggered reaction depends upon the wavelength of the reaction, and that wavelength has been found to cleave chlorine into two chlorine radicals. So in this reaction, it is also expected that the chlorine is getting cleaved into two chlorine radicals by a homolytic process. For each photon that has been absorbed in the reaction mixtures, there are millions and millions of chloromethane molecules that are being produced. So it's not like you will need, each time you want to produce a CH3Cl, you will need a photon to cleave this chlorine molecule. It's not like that. Once you have generated a couple of chlorine radicals in the reaction medium, something, a self-sustaining cyclic mechanism will take over, and these things will be produced by millions before the cycles shut down. So that is a typical signature of a free radical mechanism, where the propagation steps, as you will see, they are self-sustaining. And more importantly, if radicals are involved as intermediates, then if you push through or inject in the reaction medium some species that are known to react with radicals aggressively, they are known as the radical scavengers. One particular example that comes to mind is the air that you breathe. The oxygen, molecular oxygen, in its ground state, it is triplet in nature, and therefore when a radical is around, it just gets combined with the oxygen. So these are the radical scavengers or the radical traps that you can inject into your reaction medium, and if some radical mechanism is operating, the free agent radical that is responsible for the cyclic self-sustaining mechanism will be consumed by those radical scavengers, and eventually you will get total shutdown. The reaction mechanism will stop. The reaction will stop. Reaction শেষ হয়ে যাবে এবং সেটা দেখা যায় if you push oxygen into the reaction mechanism, then I mean not in the reaction mechanism but in the reaction vessel, purging with oxygen will shut down the whole thing. So all of these points to key free radical mechanism being operating. And if a free radical mechanism is operating, then there should be like three stages of a free radical mechanism. One is the initiation stage, where from non-radical precursors like a chlorine molecule you get new radicals, and that is triggered by either photochemistry or by thermochemistry, and that is represented in the language of organic chemistry by putting this sort of fishhook arrows. While we are familiar with this arrow, where this is the sink, this is the source of the electron pair, and that is the sink of the electron pair. So this is the source starting from maybe a nucleophile, and here it is ending maybe in an electrophile, starting from a base ending with a proton or something like that. Full headed arrow that indicates the movement of a couple of electrons, right? And here it is something which is accepting the electron pair. If you omit one of the arrowheads and make it a fishhook arrow, then obviously that means that only single electron is moving. So I have two electrons between the chlorine atoms forming the chlorine-chlorine bond. One is moving on the chlorine atom here on the right side, the other is on the left side, so you get two chlorine radicals. Now this chlorine molecule is kind of a weak bond exists between the chlorine atoms. That is because of the lone pair repulsions. The lone pairs on the chlorine atoms repel each other, and lone pairs on this chlorine atoms repel the lone pair on that chlorine atom, and therefore this bond is kind of weak, so it breaks. Its bond dissociation energy is not very high. The alternative description and the modern description is avoid both fishhook arrows and just draw only one, because it is understood that if one electron is being moved from this center onto this chlorine atom, then the other electron will obviously move in this direction, and you don't really have to draw that. If you are comfortable with this kind of notation, you are welcome to use it, as long as you don't confuse this with the polar reactions mechanism arrows where we do not use fish hook arrows. This arrow is fundamentally different from that arrow. This is a half arrow kind of thing. This is a full arrow. These are polar reactions where pairs of electrons move. These are radical reactions where only one electron moves in one direction and some other electron is moving in other direction. But because you are showing only one arrow, you might get confused whether one electron is moving and what about the other electron. The other electron, my dear, is obviously moving, but you are not showing it. If you are not comfortable with this situation, then go for that one. We have adopted this one, but one can also go for that one, the modern thing. Okay, so that's the initiation step triggered by photochemistry or by thermochemistry. And now you have your chlorine radicals in the reaction medium. Now propagation steps will take over. What are propagation steps? You can define propagation steps in this manner, that one radical is consumed in a propagation step while the other is being produced. And not only that, the product radical that is being produced in one of the propagation step will subsequently be consumed further by another propagation step. That could be the that could be the next propagation step, or if there is like 3, 4, 5, 6 propagation steps in some propagation step, maybe in propagation step 3 or 4 or 5, in that propagation step the radical that you have produced in the first propagation step will be consumed. As you will see, in halogenation there are only 2 propagation steps. So the radical that is being produced in the first propagation step will have to be consumed in the second propagation step. And in the second propagation step that you are going to generate one free radical, again that free radical will be consumed in the propagation step 1, and that is how the cyclic mechanism operates. So the propagation steps are self-sustaining once you set them in motion. So once you have got a chlorine dot, this will go on. You don't need further a source of chlorine dot, at least not from homolysis of chlorine molecule, because you are generating a chlorine dot in the second propagation step, which will come back here and do the thing all over again. So propagation steps are responsible for the cyclic mechanism, and there remains no further need for the initiation to occur. But as you are shining the light all the time, therefore chlorine molecules are occasionally being broken, chlorine radicals are being formed, and for each chlorine radical being formed, a new cycle starts afresh, leading to the formation of the vast number of molecules of CH3Cl. So propagation step 1 is basically hydrogen abstraction from methane. Cl dot abstracts this hydrogen, gives you CH3 dot and HCl. Radical consumed is chlorine dot, radical produces CH3 dot, and that CH3 dot takes part in the propagation step 2, which is the abstraction of the chlorine radical from a chlorine molecule by the CH3 dot radical to give you CH3Cl and chlorine dot, which is again consumed in propagation step 1. So one chlorine radical that you have formed that has started a propagation step and subsequently set in motion the cyclic mechanism that is going to operate will lead to a million CH3Cl molecules, and generally it is aesthetically more pleasing as well as I suppose conceptually more interesting or more understanding, if I may dare to put it, to show that as a cyclic mechanism where you start by breaking off, homolytically cleaving one chlorine molecule to give you one chlorine dot, because you are actually getting 2 chlorine dot, but let's say that I am getting one chlorine dot and the same cycle will be generated from the other chlorine dot. So this chlorine dot is abstracting this hydrogen, becoming HCl, and this CH3H that is now being taken into the form of CH3 dot. Now this CH3 dot, the upper part of the diagram consists of the propagation step 1, and then CH3 dot takes away one chlorine, gives you CH3Cl, and itself becomes, this chlorine molecule becomes the CH3, chlorine molecule becomes the Cl dot, which again takes part in the propagation step. যদি খেয়াল করো তাহলে দেখবে যে if you add up the two propagation step 1 and propagation step 2, both this actually gives you the stoichiometric equation of this transformation. So chlorine dot will vanish, CH3 dot will vanish. All that is left is CH3H plus ClCl, CH3Cl plus HC. So we can define our propagation steps in another more refined kind of manner. The sum of the propagation steps, no matter how many propagation steps we have only two here, but there are reactions where more than two steps are involved, more than two propagation steps are involved. You will see them in semester 3, not in this semester. So you sum them up, যোগ করে দাও, যদি যোগ করে দাও, you will ultimately get the net chemical reaction. The all other steps involved in the reaction mechanism are either initiation or something else, as you will see, they are termination. They are okay, not propagation. That's not propagation. তার মানে ইনিশিয়েশনে নন রেডিক্যাল প্রিকারসার থেকে দুটো রেডিক্যাল, প্রোপাগেশনে একটা রেডিক্যাল কনজিউম হলে আরেকটা রেডিক্যাল তৈরি হয়, এবং যতগুলো প্রোপাগেশন স্টেপ আছে তাদেরকে যোগ করলে আই উইল গেট দ্য নেট কেমিক্যাল রিঅ্যাকশন। অ্যান্ড দ্য থার্ড পার্ট ইজ টার্মিনেশন. Termination is when two radicals meet with each other. But that is a very unlikely scenario, because radicals are highly reactive species. They run around looking for reaction partners, and as long as there are, chlorine molecules are there, or CH3 molecules, CH3H molecules are there, methane molecules are there, they will try to react with those molecules. But at some point, the concentration of the methane or the concentration of the chlorine, or both concentrations, will be depleted, and then the radicals will meet with each other, and if they do, the termination steps will take over. তার মানে এটা হচ্ছে ইনিশিয়েশনের উল্টো। নন রেডিক্যাল প্রিকারসার থেকে দুটো রেডিক্যাল হচ্ছে, এখানে দুটো রেডিক্যাল মিলে গিয়ে একটা নন রেডিক্যাল কম্পাউন্ড তৈরি হচ্ছে, লাইক CH3 combining with Cl, CH3Cl, CH3 combining with another CH3, methane, ethane, chlorine combining, giving you chlorine molecule back, etc. But these are, very infrequent and does not take place unless either the CH4 or the Cl2 or both concentrations have been considerably depleted. That means the reaction is almost done. And it has been found that, if you in a initiation step, if you have generated one chlorine dot, the propagation step occur almost 10 to the power 6 times after such a initiation before a chlorine dot can be consumed by a termination step. So now you understand why one photon can give rise to millions of CH3Cl molecules. Termination is so infrequent and propagation is so abundant that you don't need to maintain a constant supply of chlorine dot into the reaction medium by homolyzing chlorine molecule. Once you do that, the self-sustaining nature of the propagation step will ensure that there is a steady supply of chlorine dot in the reaction medium, because chlorine dot is not getting consumed by the termination steps, and these termination steps are very, very infrequent in nature. So here we have three panels where I have summarized the initiation, propagation, and termination steps. Propagation has two steps. One is the hydrogen abstraction, the second one is the chlorine abstraction. Okay, let us move on to the thermodynamic analysis of this. Thermodynamic analysis involves analysis of equilibrium constant, which is related to the free energy change. How difficult the reaction is, or in the equilibrium, is the halogenated product dominant or the alkane dominant? So that will depend upon delta G0. So if this is our reaction, CH3H plus chlorine giving to CH3Cl plus HCl, then this is the reactant, that's the product. And delta G0 is defined as free energy of this minus free energy of this. So if this thing is more stable, lower free energy, then delta G0 is negative, K equilibrium is greater than 1, product concentration at equilibrium is more than that of reactant, or it could be delta G0 is positive, that means product is less stable compared to the reactant, equilibrium constant is less than 1, product at equilibrium is lower than reactant at equilibrium. If we break this thing down even more, then delta G0 is constituted of two components. One is the delta H0 and the other is the entropy thing, T delta S0. Entropy, we are not very comfortable with this because this cannot be calculated very easily, just like enthalpy can be. If we look at the stoichiometric net reaction, then two molecules of reactant are giving rise to two molecules of product. So we can make a grossly oversimplified assumption that entropy is not changing much, which is not a great assumption, but for our purpose, it will have to work. And in that case, the delta G0 is solely dependent upon delta H0. And delta H0, we know that it is given by some BD bonds broken minus some BD bonds formed. So if I now make an analysis where I am using X2 as my representative example of halogen, then if I know this bond energy, if I know that bond energy, and if I know that one and that one, then I am in a good position to at least make qualitative predictions about the delta G0. Considering delta S0 is not going to play a spoil sport here. It's not going to play hugely influential. The reaction is enthalpically driven. So we have this data. You don't have to remember that. But if you look at this data and try to calculate this delta H0, then you will find that all of them are exothermic to some extent or to a tremendous amount. As you can see, for fluorine is like minus 400 kilojoules per mole, whereas for bromine it is only minus 33 kilojoules per mole. But for iodine it is fundamentally different. It is like plus 55. So that's an anomaly, and that is why iodination is thermodynamically unfavorable, because delta H0 being positive and delta H0 not being that much positive or that much negative, delta G0 will be also positive. If delta G0 positive means iodination is thermodynamically unfavorable, and this reaction will not go unless when X is equal to I, you remove this HI from the reaction medium by oxidizing it or something like that. You can use HNO3 to oxidize the HI to iodine, and by Le Chatelier principle, one of the product being removed from the reaction mixture, the whole thing will now be driven in the forward direction till the whole reactant is consumed. But if you just establish the equilibrium, then this methane plus iodine, that concentration will be greater than the methyl iodide plus HI concentration, and that is why iodination reaction is not a very useful choice, because thermodynamics is against it. Other halogenations are, however, thermodynamically favorable, but fluorination, because of its explosive nature and the assorted difficulties of handling fluorine as a reagent, because it is corrosive and aggressive, very detrimental to human, and that is why fluorination is also, we don't do that. We are mostly confined with chlorination and chlorination. Now let us take a look at the kinetics. Thermodynamics is done. Let us take a look at the kinetics, but this time we are changing our model. Our model is being changed to ethane. Not much is changing, because methane, only one type of hydrogen is there. The 6 hydrogens of ethane, they are also equivalent. They are also same. 3 hydrogens here, that's a primary hydrogen. 3 hydrogens here, so those are primary hydrogens as well. So any one of the 6 hydrogens, if you replace, you will get ethyl halide and the HX. And from our previous discussion, where we took isobutane as our example, we found that harsher condition is required for bromination than for chlorination. In other words, chlorination proceeds at a faster rate compared to bromination under comparable condition. At room temperature, chlorination can be achieved, but you cannot do the bromination at room temperature. Even if you trigger the reaction photochemically, you will need some amount of heat. Why that? Why is that? For answering this question, we need to look at the propagation steps. Initiation is happening only once, and the propagation is happening millions times after that. Termination is something which is also very infrequent, so we need to look at the propagation steps. And as we know, the propagation steps are a couple of 2 in number. There are a couple of propagation steps. One is the hydrogen abstraction, and the second one is the halogen abstraction. So let us try to calculate the individual delta H0 values for all these propagation steps. For chlorination, the first step is exothermic by 21 kcal. The second propagation step is exothermic by 96 kcal. Overall, the delta H0 is 117 kcal exothermic. This will not be similar to this one because here we had methane and the bond dissociation energy of the CH3H is fundamentally different. That was like 435 here. That was only 410. For ethane, it is only 410. And it's simply because তুমি এখানে যদি H dot কে রিলিভ করো তো CH3 রেডিক্যাল পড়ে থাকবে এখানে যদি H dot কে রিলিভ করো তাহলে ইথাইল রেডিক্যাল তৈরি হয় ইথাইল রেডিক্যাল is stabilized by the inductive effect and the electron releasing nature of the CH3 group, and therefore it is easier to break this carbon hydrogen bond as you are getting a more stable radical. Therefore its bond dissociation energy is lower than that seen for methane. Fine, so we get minus 21 here and minus 96. For bromination, it is strikingly different. The first propagation step, instead of being exothermic, it is actually endothermic. And the second propagation step is significantly exothermic. Overall, it is exothermic. Overall exothermic to hobe, karon bromination to exothermic amra etage bolechi. And it turned out to be the case that the propagation step 1 is the determining step. The propagation step 1, either for chlorination or for bromination, whether you are using methane, whether you are using ethane, whether you are using isobutane, it is the propagation step 1 that is the determining step. Now for a chlorination reaction, it is immediately seen that the propagation step 1, which is the determining step, that is exothermic, and for bromination, that is endothermic. So here lies the difference which gives rise to the rate difference between the two systems. One rate determining step is exothermic, the other rate determining step is endothermic. And if you think of an endothermic reaction, then you can have basically this type of diagram. That's an endothermic reaction, right? That's your measure of endothermicity. That's your delta H0. That's positive, and this is your activation energy. So the minimum activation energy has to be at least this amount of energy. If the transition state is not above the reactant and is at the level of the reactant, that is the lowest you can think, then the reaction will go in this way, and this will require at least the delta H0 value of the endothermic reaction. So for an endothermic reaction, the lowest value of activation energy that has to be supplied, that must be supplied, is the delta H0, because otherwise this diagram does not make any sense. How can you have your product here, your reactant here, and your transition state at a lower state? Because then it is not a transition state, it is something entirely different. So transition states cannot be here. Transition states are generally like here, or if you think that the transition state is not even here, the lowest it can get is to at this level of the product, and therefore the activation energy is at least equal to the delta H. That's a given. So if you have a like a plus 42 kind of impediment in your path, the activation energy is at least 42 plus something. So that's a huge barrier that you have to surmount. On the other hand, it is exothermic, and therefore air activation energy, we have no idea what the activation energy is, but reasonably speaking, it should be much less than 42, let alone 42 plus something. 42 plus something এর থেকে তো ছোট হবেই, এটা 42 থেকেও ছোট হবে. If I draw the two diagrams here, then this is the chlorination diagram. The first step is exothermic. Do you realize that the first step is exothermic? This is where the product is of the first step. So it is lower than the reactant, so that's exothermic. For bromination, it is endothermic in nature. As you can see, the product of the first step is here, the reactant is here, so that is the first step, which is endothermic. Overall, this reaction is exothermic. That's the final product. That's the final product. That's the reactant. This is the final product. That's the reactant. Even though the first step is exothermic, it does not prevent the whole reaction from being exothermic. So the exothermic reaction means delta G0 is also negative and the reaction is a go. As you can see, it is minus 50, just like it is minus 117. But within this minus 50, there is a step which will incur a penalty of 42 kilojoule per mole at least from the reactants. It will be like more like 42 plus something. So it stands to reason that the activation energy for the rate determining step for chlorination is less compared to the activation energy for the rate determining step of bromination. And as we know that the overall rate of the reaction is controlled by what? K control করে overall rate of the reaction কে rate determining step করে. So if the rate determining step for chlorination has so much lower activation energy for the same molecule under the same condition, it has so much high activation energy for bromination, that chlorination will be faster. You can do the reaction at room temperature by photochemically triggering it, and photochemical triggering is not enough for bromination to happen. You will have to heat it to more than 100 degrees centigrade. So this is where the reactivity difference is coming from. I hope that you have understood this. Please listen to this lecture multiple times so that you get the feel of what exactly is happening here. Because as I have told you, this is the template that is going to work for you for the rest of the course and for the rest of your life if you are going to, keep swimming in the organic chemistry waters. So now comes the issue of regioselectivity. Isobutane যদি halogenation করা হয়, two different products will form. One is the tertiary butyl and the other is the isobutyl halide. There are like 9 primary hydrogens that can be replaced to give you the isobutyl halide, and only one tertiary hydrogen which is replaced to their tertiary butyl halide. How do I know that this is a primary hydrogen? You just look at the carbon with which it is attached. This is a primary carbon attached to only one other carbon. This is a tertiary carbon. So that blue hydrogen is attached to a carbon which is attached to 3 other carbons. So that's a tertiary carbon. So this must be a tertiary hydrogen. Plain and simple. This is child's play. But people tend to, get confused. What is a tertiary hydrogen? What is a primary hydrogen? Just look at the carbon, man. Just look at the carbon to which it is attached, and you will find it. You can't miss it actually. So if I think for a moment that all these 10 hydrogens, 1 tertiary and 9 primary hydrogens, they have the same reactivity under a given set of conditions, same reactivity, then the product distribution, that is the amount of tertiary butyl and the amount of the isobutyl halide that is going to be formed, will only be controlled by statistics. And in that scenario, the actual ratio of the two products should be like 9:1. Because 9 hydrogens are primary, so 9 times out of 10 I will be getting isobutyl halide, and only 1 time out of 10 I will be getting the tertiary butyl halide. For chlorination, let us check whether this is valid or not. I mean, if this premise is true, then all 10 hydrogens have equal reactivity, then only this 9:1 ratio will be observed, or something close to that will be observed. What we see is completely different. 33% tertiary butyl halide, 67% isobutyl halide. So it's like more like 1:2. So that's like from 1:9 you are getting 1:2. So undoubtedly this gives this impression that tertiary hydrogen replacement is way faster compared to primary hydrogen replacement. Because had the primary hydrogen replacement been faster, the ratio would have been like 1:100 or something like that in favor of the isobutyl chloride. It should be more than 1:9 if the primary hydrogen's replacement were faster. But what we are observing is that it is way less. It is 1:9 is expected ratio based on statistics, assuming all hydrogens react under similar condition at a similar rate. It is in fact 4.5 times lower than what we are seeing. Our expectation is 1:9, but what we are getting is 1:2. আমরা যদি এটা 1:9 এর বদলে 1:100 পেতাম, তাহলে আমরা বলতাম যে under the given set of condition tertiary hydrogen replacement এর তুলনায় primary hydrogen replacement is way faster. But this time, even though this is the major product, this should have been the major product by the ratio 9:1, but instead it is now the major product by only 2:1 ratio. Therefore, I must admit that this HA thing is getting replaced way faster than this HB. The major product is arising from HB, that is because statistically it is still winning, but HA, the lone warrior, is giving this HB a run for its money, and it is giving almost 33% of the product. So can I actually calculate that? How much more reactive it is compared to a primary hydrogen? This can be very easily calculated from this one. So expected ratio is 1:9, actual ratio is 1:2. That difference must be arising due to the reactivity difference. So the difference of reactivity between a primary and tertiary hydrogen is like 4.5 times, where the tertiary hydrogen is 4.5 times more reactive compared to a primary hydrogen under given set of conditions. But you can actually do this mathematically. So the percentage of any given chloride or halide is a combined effect of the number of such type of hydrogens. Say if we are thinking of tertiary butyl chloride, then it will arise by replacement of the tertiary hydrogen. So the number of tertiary hydrogen multiplied by the rate at which a tertiary hydrogen is being abstracted at a given set of conditions. If this is true, then 33% P-butyl chloride and 67% isobutyl chloride, if you take a ratio of them, then that is equal to rate of tertiary hydrogen abstraction multiplied by tertiary hydrogen number, that is 1, rate of primary hydrogen abstraction multiplied by number of primary hydrogens, that is 9. Now if you simplify that, you are looking to get this ratio because you are not interested in the absolute rate. You are trying to find out how much faster a tertiary hydrogen is getting replaced by a primary hydrogen. So if you take this ratio, if you try to find this ratio, then all this thing is known to you, and if you do that, then it will come as 4.43, which is very close to 4.5. You have derived it intuitionally. So our tertiary hydrogen is getting replaced by a primary by a incoming halide radical chlorination. For chlorination, this is right for chlorination because we are using the 33:67 ratio. This thing will drastically change if I take it for bromination, as you will see, because in that case the isobutyl chloride is less than 1% and this is more than 99%. So you can imagine what will happen to this number. This will become like 1600 or something like that. You can do that by putting 99 and 1 here, and then you can divide it and everything. So it will like huge, extremely more reactive. But that's a different issue. Right now we are concentrated for the chlorination reaction, where we have already established that a tertiary hydrogen is getting replaced almost 4.5 times faster than a primary hydrogen. The question is why? Why? This is easy to understand. 9:1 expected ratio, এখানে 9টা হাইড্রোজেন আছে, এখানে একটা হাইড্রোজেন আছে, so this should be like that. Reactivity difference হয়ে tertiary hydrogen more reactive হয়ে গেল primary hydrogen এর থেকে 4.5 times, and that is why the ratio has been changed to 2:1. That is also understandable. But why? Then you have to look at the RDS, and because you are talking about kinetics, you only have to take a look at the transition state of the rate determining state. What is the rate determining state? That is the propagation step 1. What is the propagation step 1? Propagation step 1 is abstraction of the hydrogen. So our model is isobutane. So if this hydrogen is being abstracted, it will lead to the tertiary butyl halide. If this hydrogen is being abstracted, then this will lead to the isobutyl halide. Let us inspect these two transition states where the dotted lines represent partially broken or partially formed bonds. We have a disappearing radical center on chlorine, and on the organic hydrocarbon we are getting at some point a radical center is appearing. For the abstraction of the tertiary hydrogen, the radical center that appears is here on the carbon, and on the tertiary carbon I should say, and for the abstraction of the primary hydrogen, the radical center appears on the primary carbon. So this transition state looks like a tertiary radical, and this transition state looks like a primary radical. We know that tertiary radical is more stable than primary radical. At least we should know that. This is the background information which you must possess to analyze this situation. If you have no idea why a tertiary radical is more stable than primary radical, then this all will mean nothing to you. Tertiary radicals, because of the electron releasing, hyperconjugation and inductive effect capabilities of the alkyl groups, are more stable compared to primary radicals, which means that if you load up on your alkyl centers or on your radical centers, removing these hydrogens, if you load up the alkyl groups, it will become increasingly more stable thermodynamically. Then if a tertiary radical is being more stable than the primary radical, then something which mimics a tertiary radical, so it is a potential tertiary radical, is also more stable than something which mimics a primary radical. That's the logic. If a tertiary radical is more stable than primary radical, then the TS, which looks like a tertiary radical, is also more stable than the primary radical. As a result, because we are starting from the same compound, we are starting from these and from chlorine dot, but we are accessing either this one or this one. If this one is more stable than this one, then the activation energy for that path will be lower than the activation energy for that path, and obviously HA or the tertiary hydrogen will be abstracted at a faster rate. There is no doubt about it, and this is where the diagram tells us so. The red thing is the tertiary hydrogen abstraction. Look at the activation energy, that's lower. The blue thing is the primary hydrogen abstraction, that is the higher activation energy. As a result, you can see that this one is forming at a faster rate compared to that one, and this one will lead to the formation of the tertiary butyl chloride. This one will lead to the formation of the isobutyl chloride. Now you can say that if this is forming at a faster rate, then should it not lead to the major product? But statistics does play a role. The reactivity difference between these two hydrogen abstraction is guided by the energy difference of this thing. If this energy difference is very large, then this will definitely emerge as the major product. But this energy difference is not that large here, because the number of the primary hydrogen is so much more, 9:1. এটা 9টা হাইড্রোজেন আছে, এটা একটা হাইড্রোজেন আছে. This is so much more favored statistically that overall these two factors, one factor that is the reactivity that favors the formation of the tertiary product, and the other factor is the statistics which favors the formation of the primary product. The statistics barely edges out, and eventually the isobutyl chloride emerges as the major product, not the tertiary butyl chloride. But the situation will change completely if you go here. If you go here, then the ratio is like 99% and less than 1%. So calculation will tell you that the reactivity of the tertiary hydrogen is way more compared to that of the primary hydrogen. It's not like 4.4 times more reactive, it's like more than, I don't know where the number is. The number is somewhere here. Can I find the number here? Here it is. It's like 1600 times more reactive than a primary hydrogen. So the which was 4.4 is now like 1600 times more reactive. So the ratio is not guided by statistics at all. Statistics is not even a minor factor here. 99% of the product is T-butyl bromide. The other 1% product is isobutyl bromide, because the primary hydrogen and tertiary hydrogen's reactivity difference is now 1600 times, which was like only 4.4 times in place of chlorination. But bromination, it is way different. Tertiary hydrogen is way more reactive, which means that the energy difference between these two transition states is very high. Why is that? This time we have to invoke the Hammond's postulate. We have been talking about the transition state, but till now we have not thought of this Hammond's postulate, which tells us that the structure of the transition state of a elementary reaction where a reactant is giving a product, it will be, the transition state structure will be closer to the excuse me, will be closer to the structure of either the reactant or the product, depending upon the difference of energy between the TS and those species. If the TS is closer to the reactant in energy, then it will mimic the reactant. If the TS is closer to the reactant, if the TS is closer to the product in energy, then it will mimic the product. And when I say product, I don't mean to say the final product, it could be the intermediate. So, by logical extension, for an endothermic reaction where the diagram is like that, this TS mimics the product because it is energetically closer to the product, the difference is only that much, whereas for reactant, the energy difference is that much. And in the reaction coordinate, you have to travel a lot of distance to access this transition state. So this is called the late transition state. Just before the product has formed, the transition state is there. And in this time, this transition state mimics the product. But if I am to draw it in a reverse manner, then the transition state arrives very early in the reaction coordinate. You have to only travel a very small distance on the reaction coordinate to encounter the transition state. And this energy difference between the reactant and the TS is way short compared to the energy difference between the product and the transition state, and therefore this transition state is also called the reactant-like transition state, or we can call it the early transition state. What does it have to do with anything here? Well, recall, bromination is endothermic, no? The first step of bromination, as you have seen, the bromination step is endothermic. You saw that here. That was the root cause of difference between the reactivity of bromine and chlorine, and that is also the root cause of difference between the selectivity. Why the primary hydrogen is getting abstracted 1600 times slower than the tertiary hydrogen for bromination and only 4.4 times slower in chlorination. This is the difference. One is in exothermic, the other is endothermic. For an exothermic step, you know, what do you know? For exothermic step, you know that the transition states are like the like the reactant. So they have a little bit of radical character, but they are mostly similar to the alkane. See where the radicals are and see where the transition states are. The transition states are closer to the alkane reactant. Therefore, they have significant alkane character and very little radical character. Their difference that is arising, the energy difference that is arising, is due to the radical character. They have some radical character, but not that much. Therefore, their difference is not that much. Therefore, this hydrogen is being abstracted only 4.4 times faster than that hydrogen. But if I am to now concentrate on the bromination, then bromination is like endothermic, no? So the two same transition states, these two transition states, they are very much closer to the reactant compared to the, the product, that is the radical, compared to the reactant. So they have very high radical character compared to alkane character. So they are mostly like radicals. These are mostly like alkanes. If the energy difference between two radicals are such that it is delta E, then greater the radical character of these two transition states, greater is the difference between their energy. And therefore, the activation energy difference between the two transition states for bromination is higher than the activation energy difference for chlorination. As a result, this radical is formed 1600 times faster than that radical, and that radical, same radical, is formed only 4.4 times faster than that radical. এই দুটোর মধ্যে এনার্জি গ্যাপ যত বেশি হবে, এটা তৈরি হওয়ার রেট তত বেশি হবে। এই দুটোর মধ্যে এনার্জি গ্যাপ কখন বেশি হবে? যত এই দুটো ট্রানজিশন স্টেটের রেডিক্যাল ক্যারেক্টার যত বেশি হবে। এই দুটো ট্রানজিশন স্টেটের রেডিক্যাল ক্যারেক্টার কখন বেশি হবে? যখন তারা এনার্জেটিক্যালি রেডিক্যালের কাছে থাকবে, অর্থাৎ তাদের ফর্মেশনটা এন্ডোথার্মিক হবে। রেডিক্যালের ফর্মেশন এন্ডোথার্মিক কখন হয়? ব্রোমিনেশনের জন্য। তার ফলে এই সব ট্রানজিশন স্টেটের রেডিক্যাল ক্যারেক্টার এই সব ট্রানজিশন স্টেটের রেডিক্যাল ক্যারেক্টারের থেকে অনেক বেশি। তার ফলে দুটো রেডিক্যালের মধ্যে এনার্জি গ্যাপ দুটো ডায়াগ্রামে এক হলেও দুটো ট্রানজিশন স্টেটের মধ্যে এনার্জি গ্যাপ দুটো ডায়াগ্রামে এক নয়। দুটো ট্রানজিশন স্টেট বেশ কাছাকাছি আছে যখন তারা মোস্টলি লাইক অ্যালকেন, less like radical, দুটো ট্রানজিশন স্টেট অনেক দূরে আছে যখন তারা mostly like radical and very much less like alkane, and therefore this energy difference will lead to formation of this radical 1600 times faster compared to that radical, while the same radical will form only 4.4 times faster than the same primary radical for chlorination. So bromine, when it approaches this molecule, it selectively picks up this hydrogen, because for bromination, abstraction of this hydrogen is 1600 times faster. But for chlorine, when it approaches, is most of the times out of 9 times, out of 100 times it picks up this hydrogen like 66%, and this hydrogen, and out of let's forget this analogy. This is not getting nowhere. So when chlorine approaches this hydrogen is getting picked up only 4.4 times faster compared to that hydrogen. Whereas when bromine is approaching, this hydrogen is getting 1600 times faster picked up, 1600 times faster compared to that hydrogen. So does statistics play a role? For sure it does. Statistics plays such an important role here that the major product arises out of replacement of this hydrogen, because এই দুটো হাইড্রোজেনের মধ্যে রিঅ্যাক্টিভিটি ডিফারেন্স থাকলেও সেটা এমন কিছু হিউজ নয়। এই দুটো হাইড্রোজেনের মধ্যে রিঅ্যাক্টিভিটি ডিফারেন্স ফর ব্রোমিনেশন ইজ সো মাচ হায়ার দ্যাট স্ট্যাটিস্টিক্স can't do anything, and greater than 99% of the product will come from here. So the energy difference between the primary and the tertiary radical is same. Delta E is the same. What changes is the activation energy difference of the two transition states. If you look at the transition states, you can in fact visually represent the radical character. If it is an early transition state, দেখো ক্লোরিনেশনের ক্ষেত্রে early transition state, কারণ কেউ কাছে আছে না, কাছে আছে, অ্যালকেনের কাছে আছে, তার মানে CH বন্ডটা এখনো ততটা ভাঙেনি, HCl বন্ডটা ততটা তৈরি হয়নি। Look at that. The CH bond is not that much broken, maybe 10%, 20% broken, and chlorine dot and hydrogen মধ্যে বন্ডটাও maybe 10% form. So hydrogen is close to carbon, therefore this del plus character is low. Compare that situation with bromination. Brominationের ক্ষেত্রে কি হয়েছে? It's like late transition state, almost radical তৈরি হয়ে গেছে, so hydrogen has already gone far away from the carbon to which it was attached and very close to bromine now, and therefore this CH distance is way higher compared to this CH distance. This HX distance is way higher compared to this HX distance, and moreover this del plus is way greater than that del plus. তার মানে এখানে র্যাডিক্যাল ক্যারেক্টার অনেক বেশি আছে, তাহলে পোটেনশিয়াল টার্সিয়ারি র্যাডিক্যাল এবং পোটেনশিয়াল প্রাইমারি র্যাডিক্যালের মধ্যে এনার্জি ডিফারেন্স ব্রোমিনেশনের ক্ষেত্রে অনেক বেশি হবে কম্পেয়ার টু ক্লোরিনেশন। ইন আদার ওয়ার্ডস, ব্রোমিন যখন আসবে ও সিলেক্টিভলি টার্সিয়ারি হাইড্রোজেনটাকে তুলবে, ক্লোরিন যখন আসবে ও অতটা সিলেকশন কিছু করতে পারবে না। তার মানে ক্লোরিন ইজ মোর রিঅ্যাক্টিভ অ্যাজ উই হ্যাভ অ্যানালাইজড ফ্রম আওয়ার প্রিভিয়াস স্লাইডস, অ্যান্ড ইন দিস স্লাইড উই আর গেটিং টু আন্ডারস্ট্যান্ড ওয়াই ব্রোমিন ইজ মোর সিলেক্টিভ। এখান থেকে কোয়েশ্চেন আসে, বাট মাই রেকমেন্ডেশন ইজ দ্যাট ইউ অ্যাভয়েড দিস কোয়েশ্চেন. Well, that is because you have to draw all these diagrams and write out all these things, exothermic, endothermic. You have to invoke Hammond's postulate, draw the transition state to show যে এর radical character কম or radical character বেশি. Not a very good question to answer. For 3 credit, it's not a very good question to answer. The final thing is that if I am to halogenate an optically active ketone, where I am talking about abstraction of a hydrogen from a chiral center. So basically I am rupturing a bond of the chiral carbon and hydrogen. What do I get? Because I could theoretically get retention, hydrogen যেখান থেকে বেরোচ্ছে সেখানেই ঢুকলো. I could theoretically get inversion, that means ওখানে hydrogen যে ফেস থেকে বেরিয়েছে তার উল্টো ফেসে ক্লোরিনটা ঢুকলো. Or I could get both the inversion and retention, 50% each, that means racemization. That is exactly what I get. If I take an enantiomer variety of this optically active hydrocarbon where already there is one chlorine being present, that is because I want to make it chiral. You could take it something different, you could take it totally different something, but let us take a chlorine here because this is an example that we have found in literature. So chlorine, photochemical chlorination is giving rise to replacement of this hydrogen. That's the tertiary hydrogen, so it's like more reactive than any other hydrogens here. These are like the primary hydrogens, these are like the secondary hydrogens. So the tertiary hydrogen is more reactive than the secondary is more reactive than the primary. That is because the radical stability order also follows the same trend. Tertiary radical is more stable than primary. Secondary is more stable than primary. We understand why this is so, and that is why the reactivity rate also follows the same trend. So this will be replaced, and this replacement gives me like two equal mixtures of two enantiomers, where I get both the R as well as the S dichloro compounds. How can I explain this? The radical intermediate that is being formed, therefore, in the reaction mixture, the radical intermediate, therefore propagation step 1 will abstract this hydrogen. So the radical intermediate will form and it will abstract the chlorine. That has to be achiral. And this is planar and achiral, and therefore this is speaking of this chlorine either from the front face giving rise to this molecule, or from the back face giving rise to this molecule. This is planar in the plane of the paper, therefore it has two faces. One is towards you, the front face, the other is away from you, that is the rear face. And because it is achiral, it has got absolutely no preference whatsoever of picking off this chlorine from any of the two faces. So je kono ekta face theke nite pare, and it will give rise to both the R as well as the S isomer. If I draw this in this plane, like xz plane, then xy plane, then from plus z direction or from the minus z direction, it can abstract equally happily it can abstract, and it will give rise to this compound. So that's it. So there is racemization, and this is what you expect in absence of any other complicating factors. And this kind of rules out the alternative propagation sequence. See, the propagation sequence that we have talked about is basically propagation step 1 is hydrogen abstraction, the propagation step 2 is halogen abstraction. What if it was the other way around? What if X dot, instead of this hydrogen abstraction, it would have reacted with this alkene, so I would have got Rx and H dot. The H dot would have reacted with XX to give me HX and X dot. First of all, if you analyze these two scenarios for a given alkane, the thermodynamics is all over the place. In the actual sequence of methane chlorination, let me go back here. In actual sequence of methane chlorination, you have overall delta H0 is negative, and both the steps that you calculate your delta H0 value, that those will be like negative. But for this one of the steps will be endothermic. Moreover, more importantly, if this were to happen, যদি এটা হতো, তাহলে খেয়াল করে দেখো এই হাইড্রোজেনটার সাথে কাইরাল কার্বনের যে বন্ড সেটাকে আমি রাপচার করছি, বাট at the same step I am forming the bond with the X dot. So when X dot is forming the bond with RH, it is chiral. It is not that যে R dot তৈরি হচ্ছে অ্যাকাইরাল হচ্ছে এবং তারপরে X এর সাথে X2 এর সাথে রিঅ্যাকশন করে RX তৈরি হচ্ছে. It's not like that. When it is chiral, it is forming the bond with X. So there are two possibilities. When this chlorine dot is reacting with this carbon dot, if this is true, then when the chlorine dot is reacting with carbon dot, not carbon dot but the CH bond, then either I will get retention, where hydrogen will be replaced and chlorine will enter from the same phase in the same step, or I will get an inversion, where hydrogen will be replaced and chlorine will be introduced in the molecule in the same step from the different phase. Because chlorine is interacting directly with a chiral molecule, we cannot have racemization here. We will have either retention or inversion. We cannot have both. Both we can have only when we have made an achiral intermediate starting from a chiral compound. Just like we have done here, the achiral free radical intermediate is formed and it is reacting with chlorine with both of its faces with equal probability. But if this alkane itself is reacting with chlorine dot, then either this one will form or that one will form, if this mechanism were true. But what we are actually getting? Are we getting only this compound? No. Are we getting only that compound? No. We are getting racemic mixture, and that racemic mixture cannot form via this propagation step. So this premise that this is the propagation sequence is all wrong. That is not the correct propagation sequence. Therefore, the propagation sequence that I have proposed earlier, that is hydrogen abstraction followed by halogen abstraction via the intermediacy of R dot, that is the correct one. So I hope that you have enjoyed this lecture. I have done this thing deliberately in English. Please let me know whether you have faced any problems in following the concepts. Um, and do listen to it multiple times, comparing the study material uh, while listening to it, and frequently pausing and thinking of whatever being said. Thank you for your patience, and I will be seeing you in the next one.